agree.
Yeah.
But that's another function.
Yeah. Okay, maybe you let's discuss this one.
That's like
Yeah.
Okay, so we're happy to have Tianli Wang from Harvard University, and she's going to tell us today about a CFT dual for celestial MHV amplitudes.
Thank you so much for inviting me to speak here. And today I'm very happy to tell you about a CFT dual we constructed for celestial MHV amplitudes. So this is based on this paper from last March in collaboration with Melton, Atul Sharma, and Andy Strominger. And the key objects that bridge the CFT dual we built and usual class-based amplitudes are the so-called leaf amplitude. These are partial amplitudes associated to individual hyperbolic slices in Minkowski space. And these were first introduced in this earlier paper by my collaborators. So before going on to talk about everything appearing in my title and also what leaves are, what leaf amplitudes are, let me start with some introduction and background. Click here. Okay, great. So the program of celestial holography is concerned with the duality between gravity in 3+1 dimensional asymptotically flat spacetime and a CFT dual on the 2-dimensional celestial sphere at the boundary of this spacetime. This duality also holds in higher dimensions, although I'll focus on 2D in my talk. So in the bottom-up construction of celestial holography, we match celestial amplitudes, which are flat space amplitudes written in a particular basis, not the regular plane wave basis, but another one that I'll tell you about in a minute, so that they transform like CFT correlation functions. We map these onto CFT correlators on the celestial sphere. And in this process, the matching symmetry groups on the two sides play an important role. So I'll focus on SO and PMLs in my talk, won't consider dynamical gravity. So we'll only focus on the global part of the symmetry groups, which is Poincare in the bulk. So Lorentz and translations, and the global part of the 2D conformal group on the boundary. Okay, so a basic but important fact about this correspondence is the isomorphism between Lorentz symmetries, the Lorentz group, and the conformal group. But an immediate question you might ask here is then, what about translation symmetries? What role do they play in the boundary CFT? And indeed, translation symmetry doesn't look very natural from the CFT point of view, and they can, in some sense, impose too many constraints on observables in the CFT. And one important way to see this is they force celestial amplitudes, especially some low point ones, to be singular. So like I was saying, celestial amplitudes are flat space amplitudes written in a particular basis so that they transform like CFT correlation functions. But some of them don't quite look like usual CFT correlation functions, but they contain these kind of singularities in where two operators collide. So here I'm being kind of schematic here. C is a coordinate on the celestial sphere, and ij label different operators. So these delta functions come from the momentum conserving delta function in momentum space amplitudes, which are always there, which of course result from bulk translation invariance. But our usual CFT correlation functions don't have this type of singularity, and this prevents a direct, easy construction of a dual CFT. So this is not great. And this suggests that these bulk translation invariant amplitudes might not be the best to consider, but we might want to work with amplitudes that are not necessarily translation invariant, but still preserves Lorentz invariance and are smooth and more natural, and in some sense more fundamental building blocks for celestial holography.
Can I ask you a question?
Please.
So in this idea, can you do the same trick but preserving local conformal invariance, namely the full super rotation, not only Lorentz invariance?
That's a good point. So here I'm not really considering dynamical gravity, so there's no super rotation.
Okay.
Yeah, but if you consider dynamical gravity, you can definitely make that choice. Yes.
But you preserve the local Katsumudi symmetry, right, when you do this. So that's the analog. And
Yeah, exactly. That's right. Thank you. Yeah. Okay, so there has been a lot of recent work in this direction. For example, all these people explicitly break translation invariance by introducing a non-trivial background to the theory. And in particular, this paper by Steenberger, Taylor, and Drew constructed smooth amplitudes dual to correlators in the Liouville CFT. And this is a major inspiration for us. And Liouville will also turn out to be the main constituent of our dual CFT.
They break translation invariance putting this axial field, this background.
Yes, that's one way to do it. Exactly. Yeah, like background scalar, and so on. Right. So yeah. Although our approach will be very different from this, we don't introduce a non-trivial background. And some people change the external legs of scattering by doing shadow and light transforms on them and obtain smooth amplitudes. And in an earlier paper from our group, we also constructed a family of non-translation invariant vacua to scatter around, the so-called hyperbolic vacua. And these are analogous to De Sitter vacua. The De Sitter alpha vacua. Okay. So these all deal with translation invariance in a very nice way, but they're all somewhat roundabout. And more importantly, they don't recover translation invariance in the end explicitly. So in the work I'll tell you about today, we use a very different approach with leaf amplitudes, first introduced in this paper here. And our main achievement using leaf amplitude is we give a direct two-dimensional reconstruction of translation invariant for the amplitudes, at least for gluon MHV amplitudes as a starting point. Okay, so let me tell you a little bit about what leaf amplitudes are, and I'll make all this more precise with equations later on. So here I drew the Minkowski diagram of a flat space. Sorry, Penrose diagram of Minkowski space. So I labeled the future and past time-like infinities, spatial infinity, and maybe more relevant to my talk, the non-infinities. I also drew the light cone of the origin. So Minkowski space adopts the so-called hyperbolic slicing, where you can fill in the entire space-time with Euclidean ADS3 or hyperbolic 3 slices inside the future and the past light cone, and De Sitter 3 slices outside the light cone. So these slices are preserved under Lorentz transformations, but they're mixed among themselves under translations. So you can think of the slicing as a fancier version of slicing up Euclidean R4 with spherical shells concentrated at the origin, which are also preserved by all the rotations around the origin, but the slices mix among themselves under translations. This is just in a different signature. So in this paper, the authors broke up the full selection amplitude as an they wrote the full selection amplitude as an integral over the entire space-time and took only the part of the integral over only one slice like this and obtained a leaf amplitude. So naturally, leaf amplitudes break translation invariance while preserving Lorentz invariance. So that's great if we want to construct a CFT dual for them. Okay, so that's exactly what we did. And just reiterate, we gave a direct 2D reconstruction of translation invariant for the amplitudes. So we tackled the tricky translation invariance head on instead of circumventing it by, say, introducing a background or transforming to another basis. So this is a bit more direct. More precisely, the holography is achieved in 2 steps. In the first step, these leaf amplitudes being smooth objects allowed us to find a CFT dual for them. And this will be the main part of my talk. It's to tell you about the CFT dual and the holographic dictionary. And the second step is after obtaining leaf amplitudes from this CFT dual, we can combine them to reproduce the singular slash amplitudes, meaning translation invariance emerges. So that's great. Okay, so here is the outline and basic line of logic of my talk. We want to find a CFT dual for celestial amplitudes, but these guys are singular, so it's hard to directly find a CFT. Leaf amplitudes can serve as a nice intermediate step between these, being smooth and fundamental building blocks for celestial amplitudes, for which we found a relatively simple CFT dual. And this CFT contains two parts. One is with free fermions.
Sorry, but only for the maximal differential violated set.
So far, yes. Yeah, exactly. I'll make a comment about that at the end of the talk too. So what the first sector is free fermions, which is responsible for the spin structure of spin in the amplitude, and the second one is Liouville theory. So my talk has two main parts. In the first part, I will review the relevant basics of celestial holography, in particular celestial amplitudes, and tell you how to extract leaf amplitudes from these. And in the second part, I'll tell you about new results on the CFT dual. Okay, any other questions before I start with reviewing celestial amplitudes? Good.
That's all the field content you will consider? Free fermions and Liouville only?
Yeah, exactly. That's enough. In this bottom-up construction, that's enough to reproduce the leaf amplitudes.
Thanks.
Thanks. So yeah, I'll start with the left side of the chain and go to the right. Usually when we consider scattering, we work in momentum space with plane waves. So by the way, here I will focus on massless scalar field, which is relevant for my talk. So plane waves provide a complete basis to the Klein-Gordon equation, and they also transform nicely under translations. But in the context of celestial holography, we might want to work with some other basis that has nice transformation properties under the symmetry groups being matched in the holography instead of translations. So that is with nice transformation properties under Lorentz transformations or conformal transformations. And such a basis is provided by the conformal primary wave functions. So each conformal primary wave function is labeled by a weight delta and a unit non-momentum p hat. It's the Mannich transform of plane waves with momentum omega p hat. So omega is the energy, and epsilon is a small positive regulator for the integral here. And so in going from the plane wave basis to the conformal primary wave function basis, we create the omega energy label for delta the wave, and these diagonalized boosts along p hat. We can perform the integral in closed form and obtain this expression. It's a constant dependent on delta that I'm not writing out explicitly over p hat dot x. Oh, by the way, x is just coordinates in Minkowski space with some I epsilon prescription to the delta. So let me mention two important properties of these wave functions. So first, each of them transforms like a conformal primary with conformal primary operator with weight delta at ZZ bar on the celestial sphere. And ZZ bar is related to p hat via this relation here, where epsilon, this is a curly epsilon, and it's different from this epsilon here. It takes values plus or minus 1 and indicates whether the particle is incoming or outgoing. Okay, so let me explain the geometry a little. So if we take the three spatial components of p hat, so in R3, you can think of the celestial sphere as the infinitely large sphere, two-sphere at infinity. And the direction of p hat points to a point on the celestial sphere, and that's parametrized by ZZ bar, the stereographic coordinates on that sphere. So that point is exactly where this particle enters or exits the spacetime, and it's also where the corresponding CFT operator is inserted. Okay, so the second property I wanted to stress is that these provide a complete basis for the wave equation when we choose the weight to lie on 1 plus I times a real number, so completeness relation. Okay, so now that we have a nice basis, let's scatter in it. So we can obtain celestial amplitudes by performing many transforms on momentum space amplitudes, where we just have one many integral like this for each particle. And by construction, celestial amplitudes transform like CFT correlators with weight delta and some spin. But like I mentioned, some of them, especially the low point ones, don't quite look like usual CFT correlators, but they contain these type of singularities at low points. So let me explain what I mean exactly by these by giving you a concrete example. So the example is for scattering 3 gluons in pure mLs. So I'll present the calculation on this page in 2-2 signature, or equivalently continuing to complex momenta. This is just a technical comment. The main reason is just all 3-point amplitudes for massless scattering in Minkowski space vanish. Okay, so this is an example of a maximally helicity violating amplitude, or MHV amplitude for short, by which I just mean we scatter a bunch of gluons with only 2 of them having negative helicity and all the others positive. So this is the simplest 3-point version, although the n-point version, which we'll see in 2 slides, is actually not too much more complicated. So these have very simple expressions like this, and we can also build all other tree level amplitudes out of these MHV ones. So these MHV tree level amplitudes are what I'll focus on in my talk. Okay, so at 3-point, this is just the simple prefactor involving the energies of the particles and the z's, which parameterize the direction of the non-momenta, where z12 is just z1 minus z2 and so on. And there's, of course, the momentum conservative delta function. I also wrote this in spinor helicity notation for those familiar with it, but I won't be using this notation in my talk. So to get the corresponding celestial amplitude, we do 3 Mellin transforms on the omegas here, which of course also appear in here, and obtain this expression. It looks slightly complicated, but it's just the holomorphic part of a usual CFT correlator dressed with a bunch of delta functions and theta functions and so on. So I introduced some new parameters here. So these resulting conformal primaries have spins -1, -1, +1. Delta is given in the parameter in the Mellin transforms, and the weights are defined as usual. ABC, A bar, B bar, and C bar are just these combinations of the weights, and beta is related to the sum of the anti-holomorphic weights like this. So let me draw your attention to the 2 properties I mentioned on the last slide in this correlator. So first, by construction, this transforms like a CFT correlator, like a 3-point CFT correlator of operators with these spins and some deltas. Deltas are kept arbitrary at this point. And also note these delta functions here. So this is exactly what I meant by saying the low point celestial amplitudes are singular before. So these are remnants of performing Mellin transforms on the momentum conserving delta function here, which comes from bulk translation invariance. So again, the origin in the bulk is very clear, but our conventional CFT correlation functions don't look like this at all. So this tells us that we might need to deal with bulk translation invariance in a more proper way to understand how this can come about. And that's where leaf amplitudes come to rescue.
Sorry, what does it mean delta Z bar? So are Z and Z bar complex conjugates?
No, so this calculation is in 2-2 signature. So we've continued to complex momenta. So Z and Z bar are real and independent.
And the bars in the Z12 bar, is it the absolute value or is it?
Exactly. So that's the absolute value of the Z coordinates. There's no Z bar in here. Exactly. That's a good point that I should have stressed. Okay, yeah. Any other questions before I go on to leaf amplitudes? So
But the two signature, you mean that means that you got the Lorentzian to the conformal group, which is expected in the mapping of the conformal group.
exactly.
Lorentzian.
So that would be if you attempt to do the whole leaf amplitudes construction in 2-2 signature, you will get like a Lorentzian torus on the boundary, exactly like you said. But I'm only presenting like this example as an example for a singular slasher amplitude in 2-2 signature, and the rest of the calculation in my talk will be back in Minkowski. Although eventually we still have to relate to 2-2 as you'll see in a minute.
Okay.
Okay, any other questions? Okay, so now we're counting on leaf amplitudes to save us. So this is where we are. We finished reviewing slasher amplitudes and now leaf amplitudes. So, oh, sorry. So as I mentioned, I'll focus on MHV tree level amplitudes in my talk. And here is the endpoint version of the 3-point MHV amplitude that you just saw a moment ago. Here's the Park-Taylor prefactor and the momentum conserving delta function. So to obtain the slasher amplitude, we do n Mellin transforms on all n external legs on this amplitude. And the key to extracting leaf amplitudes is to write these delta functions as an integral over the entire spacetime and taking only the part over one leaf. So let me quickly remind you of the geometry here. So we're slicing up the entire spacetime with like ADS leaves inside the light cone and de Sitter leaves outside the light cone. By leaf, I just mean hyperbolic slices. And for reasons that I'll explain in a minute, I'll only focus on the ADS slices inside the light cone for now, and which will parameterize, we'll put a coordinate x hat on the ADS leaves, and tau is the time direction. So the bulk coordinate x is tau times x hat. So we can write the delta function in the usual way as the integral of plane waves. And then we can break up this bulk integral into one part over the time direction tau, labeling different leaves, and a part over a unit ADS leaf like this. This is the so-called leaf decomposition. And I'll shade everything related to one leaf green on this slide. Now, in going to the next step, we perform these Mellin transforms on the plane waves in here. And like I showed you for the conformal primary wave functions of massless scalars, we obtain exactly those here. So these are conformal primary wave functions, but I have pulled out factors of tau here because x, big X is proportional to tau. So these guys are homogeneous, and I can pull out factors of tau to get this factor out front. To remind you, beta is this expression here. So now the integral factorizes nicely. We have a part over tau and another part on one unit ADS slice. These z factors just come along for the ride. And it turns out that we can do the tau integral and obtain a delta function in beta, and the rest is our leaf amplitude.
And this factorization, so there's in like the top right thing that you've shaded in green, you have that tau sitting that's e to the I p dot x hat tau.
Yep.
This factorization is like sensitive to what amplitude you're doing, right? Like I think for MHV it factors, but it's not obvious that it factors for like a very general amplitude. Right?
Exactly, totally. This has to do with the interaction vertex being local in some sense for MHV. But say like when you even go to like N MHV, it's not obvious. This it's actually easy to see it doesn't factorize in the similar simple way.
Okay.
Yeah. Okay. So I've been ignoring the de Sitter slices for now because we don't know how to directly obtain leaf amplitudes on those slices or how to relate them to the ADS ones. Eventually, the better thing to do would be to continue to complex momenta again or go to 2-2 signature. The advantage of 2-2 space is there's a similar hyperbolic slicing, but we can slice up the spacetime both inside and outside the light cone with only ADS slices, with different signature, but only ADS. And we have a simple relation between the leaf amplitudes on the slices inside and on the slices outside the light cone. Unlike here, we don't have a simple relation relating those two. But the construction of leaf amplitude of the leaf CFT, of the dual CFT, which is the main part of my talk that I want to get across, go through without making reference to complex momenta or 2-2 signature. So I won't sidetrack and will only stay in Minkowski space and focus on the ADS leaves for now. Okay, so to write it out explicitly, here is our leaf amplitude. So it has two parts. One is the MHV prefactor with all the omegas, encoding the spin information, and the other one is a product of scalar conformal per array wave functions with all the taus in the denominator and with the common bulk point integrated over a unit ADS leaf. Okay, so let me make 3 comments on these leaf amplitudes. First, each of them is integrated over only one ADS leaf, so they manifestly break translation invariance and turn out to be smooth. So that's great. That's exactly what we wanted. And second, they sum up to translation invariant celestial amplitudes, which are singular at low points. So that just amounts to this relation between a celestial amplitude and a leaf amplitude. So in this paper, the authors evaluated the 3-point leaf amplitude explicitly, show that it's smooth, and then plugged it back into this relation and show that you get the singular celestial amplitude with all the delta functions and theta functions and so on. So it works out pretty nicely. So this is a good point to stress again that this is the main way in which our work based on leaf amplitudes differ from works before dealing with translation invariance, is we recover translation invariance in the end explicitly. Okay. So the third point I like to mention is that this integral, the scalar part, turns out to be exactly a scalar contact Witten diagram, because each of these factors in the product is just a bulk-to-boundary propagator in ADS, with the bulk point given by x hat and the boundary point by z bar, which are related to p hat. So this is very nice. These objects are well studied in ADS CFT and allows us to make contact to ADS holography. So don't worry if you're not familiar with ADS Witten diagrams though. By ADS Witten diagram, I just mean literally this expression in my talk. Okay, so now we have finished the whole review part. Any questions before I go on to tell you about the CFT dual?
Yeah, wait, when you go back one slide. So to make the connection between ADS Witten diagrams though, right, you have to identify the full conformal dimension of an ADS Witten diagram with like the right moving conformal dimension.
Oh, yeah,
Yeah.
exactly. So yeah, there's a mismatch there, which it works out like very nicely with these omegas.
But in particular, yes. In stripping off the beta, this delta function, right?
Yeah.
You actually chose a particular way
Yeah,
of, assigning weights to this. Yeah, okay.
yeah,
It-
exactly.
you have to do it this way, or you can do it any other way.
Can you do it any other way? Sorry, are you asking about, wait, can you repeat the question again?
So when you actually calculated right from the first line to the last line,
Yeah,
right, in splitting the leaf amplitude off of this delta function,
off of,
the delta function of
Delta
beta,
beta,
you
yeah.
made a particular choice for what the weights of, how the weights appear in the green,
yeah,
right? Because I could have used that beta 0 to rewrite it in a different way. Right, like it's a very symmetric.
You're saying you could like rewrite what's in the green by working mod the relation beta equals 0?
Yeah. And I guess that my question is
I
like,
see,
because
okay.
now you're trying to just calculate the green thing, right, from some sort of first principles thing. Did I need to make this particular choice? Or would it have worked if I had, worked,
if you add in like,
if I worked mod beta equals 0?
yeah, exactly, like add in like functions that vanish on the support of the delta
Yeah.
function. I think you can do that, but we do want our leaf amplitudes to obey some nice properties, like nice soft, soft limits and stuff.
Yeah.
And that's worked out in like another paper by my collaborators in 23. So this a priori is not unique, but for MHV amplitudes, this turns out to be the nicest thing we can write down almost, but you can definitely make other choices. And for like more complicated non-MHV amplitudes, you almost certainly have to like play around with other choices. Okay. Any other questions? Okay, so I finished the review, and now let me go to new results on the leaf CFT. The punchline is we give a CFT construction whose correlation functions reproduce leaf amplitudes. And this CFT contains two sectors, one with free fermions, which reproduces the spin part of the leaf amplitudes, and the other one is Liouville theory, which reproduces the scalar part.
So, but only in the very large, in the large ND.
Exactly, yes.
Sorry, what was the caveat there?
Only in the, I mean, if you see this per factor, can only be recovered in the large ND.
Yeah, otherwise you have a bunch of other terms, like higher trace.
You have contraction for the currents.
Yeah, it'll be clearer in like one slide, I think. So leaf amplitudes divides nicely into these two parts, which are reproduced nicely by the two sectors in the leaf CFT. And this part would be the part doing the more heavy lifting, because as we recall, we obtained these conformal primary wave functions by doing many transforms on the plane waves coming from the delta functions. So that's the part encoding translation invariance. Okay. I have enough time. So the construction of the free fermion sector is relatively well studied in the literature and follows these references. So we have n free fermions where I runs from 1 to n, and n is identified with the n of the ISO n Young-Mills theory we're working with, plus a fermion eta of weight -3/2 0, which you can think of as like a field from a BC system. So these have the following LPs. psi OP is delta ij over z minus w, and the eta OP is finite. I just wrote the first term in the Taylor expansion. And we can construct these following currents out of these fields. So we can construct Cost-Moody currents for SON, which we call J and have weight 1, 0. These are a half SON generators in the fundamental red, constructed with 2 sides. And this will provide the spin part of positive helicity gluons. And we can also construct some other currents with weight -1. These are J bar and are just J dressed with eta bar. So J has weight 1 and eta has -3/2. And you can plug it in and see the weights check out. And this gives the spin part of negative helicity gluons. By the way, this is just the usual construction of WCW model. And so now we can compute the OPs of the current. And I've copied over the field OPs and definition of the currents here. The JJ OPE just gives a Cost-Moody algebra with level 1, where these F are SON structure constants. The J bar OPE is obtained by simply multiplying the first line with partial eta. And I won't get into how to obtain the J bar OPE, but I'll make a related make a comment on a related selection rule after showing you the result. So the result for an endpoint correlation function of the current involving 2 J bars and any number of J's in the larger limit is exactly the spin part of the leaf amplitude.
Can I ask you, just understanding it?
Yes.
So first of all, this is for the MHV sector,
Yeah.
so it's in a large limit also. But also this is not dual to Yang-Mills only, no? You need some extra field, right? Because the OP of JJ will produce, because of the level 1, some scalar in the OP. So JJ gives a J
Yeah.
plus something at this of scalar, right? Because it has level different from 0. So it will produce a mix between 2 gluons and something else, apart from 2 gluons, right?
Wait, so here the level actually doesn't play a role in this final.
In this, no, but now if you factorize it out, yes.
If I factorize it out, wait,
Yeah,
do you mean?
just factorize this endpoint function and see all the intermediate steps. You will see,
Okay,
you will see an extra J, of course,
Sure.
but also a term that doesn't have a J, has something else.
Yeah,
And it's
exactly.
a scalar.
Mm-hmm.
So you should be able to interpret this scalar from the bulk point of view. The constant limit of 2 J's
Yeah.
gives a J and plus something else.
Yeah, I
That's
see what
something
you
else.
mean.
Yeah,
But is
Yeah,
it a
so-
double trace?
I don't know what it is, but this is double trace. I don't
Yeah,
think
it's
so.
in,
I just-
Exactly, I think it's double trace
double
and
trace, right?
so it's in the dot here and vanishes in the larger limit.
No, it's at the same order in N. I mean, it's a OP of N, right? It's N. I mean, the OP of JJ gives a J and a
you're talking about
central
supermarket.
term that has
Yeah.
no, it's the same hierarchy in N. There's no double trace. Take a SUN current with another SUN current, it will give an order 1 current plus an order 1 scalar.
Okay, I thought that was higher than 1 over N, but I might be mistaken, yeah, what you just said makes sense. But so I don't think we're trying to so in this is like a bottom-up
No, of
construction
course, I mean,
for-
this is totally fine. The question is, what I'm just trying to understand what it would be the dual.
what it could be in the.
Yeah, the dual gauge theory. Would it be only pure Yang-Mills or Yang-Mills plus some axion or?
Yeah, exactly. So I'm not sure. We didn't really look into that. I believe in a paper by like Walker Melton, one of the authors, and Shruti Narayanan. They have a discussion about like a scalar with like higher order connected term that might have that interpretation, but yeah, I'm not really sure. Okay. All right, so this correlator, this endpoint correlator with two J bars and a number of J's is exactly the spin part of leaf amplitudes. And here, note that I dropped all the color indices, only kept one color ordering, also dropped all the higher order terms in 1/n. Let me see if I wanted to say something else here. I think that's good. Okay, any questions, any other questions about the free fermion sector before I go on to Liouville? So this is where we are. We completed the first part of the correspondence, and now let's go to the second sector. So to get the scalar part of leaf amplitudes from the Liouville sector, the key ingredient is to show the equivalence between the correlation functions of light operators in the classical limit of Liouville theory gives the contact Witten diagrams. So let me give you a lightning review of Liouville theory before showing you how to do that. Liouville is a very interesting and rich theory. It's an exactly solvable 2D CFT that has many aspects, but here I'll only give you a review of the directly relevant aspects to my talk. So the action is given by this expression here, where we have like a usual connected term for a complex scalar and an exponential potential. The semiclassical intuition for this theory is e to the phi gives the metric with constant curvature on the sphere that we put the theory on, where the constancy is imposed by the Liouville equation, which says the curvature equals -8 lambda, where lambda here is the cosmological constant. And B appearing in the denominator in front here plays the role of H bar. And we will work in the limit where B goes to 0. So that's the classical limit of the theory. So the central charge is related to P by this. And in the classical limit, we take B to 0. The central charge diverges. In the meantime, we keep lambda fixed. Okay. So by the way, this is all known result from that you can find, for example, in these papers. So the conformal primaries in Liouville are the vertex operators e to the alpha phi or B, where alpha is related to the weight. And in the classical limit, there's a particularly interesting family of operators, the so-called light operators. So these operators have alpha proportional to B. So sigma is finite and alpha goes to 0 in the classical limit. And these operators have particularly simple correlators because they're so light that their presence doesn't change the saddle, but they just sample the solution. So before going on to explain this correlator, let me show you the saddles or the solutions. So phi is labeled by G and SL2C group element, and is related to the usual stereographic metric here with some constant here by just choosing G to be 1. So if you exponentiate this, as we said on the last slide to get the metric, you find the stereographic metric. So now let's unpack this light correlation function of light operators a little. So if you ignore the integration over G and the G's here for now, it's just the on-shell action multiplying the light operators themselves, where for phi, you just plug in the solutions. But now you also need to integrate over all the solutions related to each other by SL2C like this. And that guarantees the resulting correlator is conformally invariant. Okay. So now the key step is to show that these correlators that I copied over here give you contact Witten diagrams or the scalar part of leaf amplitude. Similar integrals appeared in this paper by Bradell, Krasnov, and Levine. And I copied over the saddles here. So to begin with, I put out the on-shell action exponentiated because it's SL2C invariant. And the SO2C group manifold factorizes into two parts. One is SO2 and the other one is ADS3. It turns out that this integrand is SU2 invariant because intuitively SU2 just rotates the sphere without deforming the metric on it. So that preserves the integrand, which has interpretation of the metric. So the SU2 part factors out, and we only have the ADS3 integral. So that's looking nice. And what's even nicer is when we plug in the saddles here, while choosing an appropriate parameterization for the SL2C group element G, we obtain exactly ADS bulk to boundary propagators. So this is very nice. So in total, we have the product of n ADS bulk to boundary propagators with the common bulk point integrated over ADS. And that's exactly the scalar part of Liouville amplitudes. So here I have a technical slide, but I think I'll skip it. For those interested in the detail, I'll just point out that the key parameterization comes from the Iwasawa decomposition of SL2C group elements, where G can be written as a product of an SO2 matrix and two matrices parameterized by rho and y, where rho and y are exactly Poincare coordinates on ADS. Okay, so the upshot is we were able to reproduce the scalar part of Liouville amplitudes with light correlators in Liouville. Okay, so now it's finally time to put these two sectors together. And here is the holographic dictionary.
So would you expect that the finite B correction will be loop corrections in the?
That's a really good point. So in the paper by Stiefberger, Taylor, and Drew, they actually considered like loop amplitudes with a non-trivial background and matched part of that amplitude onto part of Liouville amplitude, Liouville correlators. We go away from the go to the next order in B. So that's a very valuable piece of intuition, and I think because so far everything we have is tree level, and when we want to go to loop level, we'll try to turn on B in Liouville theory, and yeah, it's hopeful that that gives you a loop, like YAML's loop amplitude.
It's funny because it's different from ADS-CFT in the sense that finite B would be 1/C finite correction, but it's still being at large n.
Yeah, exactly. Yeah, we take like larger limit, the small b limit, and it'll be interesting to work out the exact correspondence between the parameters on the two sides of the duality, like we know in ADS CFT. Yeah, that's a really interesting thing to work on.
There's no competition between N and B here, right?
No competition.
There's no N and B, the limit are taken separately.
Yes, exactly. Yeah. Doesn't matter the order. Yeah. Okay.
Just because the factorized property, but at loop level, you expect there to be competition.
What do you expect?
You want to take
that-
NG50 first and then take B to be 0 or the other way. Or in other words, how should I think
Yeah.
about this on the previous slide, this correspondence? If one to think about a finite A and B,
Yeah, exactly.
what you have shown is what kind of limit of that finite correspondence.
I'm not sure. So they're definitely not MHV amplitudes anymore, but it's if you just take.
Do you have to focus on planar amplitudes in the talk? Do you expect this to
Well-
work more generally without planar or
I'm not sure. I think like to get to say like go beyond MHV or to add in loops, it's not obvious to me just naively taking like N to be finite or B to be finite would give nice results. So taking B to be just like taking B to be finite, that seems to be like a more controlled thing to do, according to like Taylor and Friends paper. But going away from and going to infinity, yeah, I'm not exactly sure because then you get like all these higher trace terms and they definitely correspond to, they probably correspond to like non-gluon field in the bulk. Yeah, I remember like seeing like we were thinking about this and seeing something that behaves like a conformal graviton.
So
And
do you
so
think the free fermion sector will get modified?
Yeah, exactly. Yeah. Yeah, that's right. Okay, any other questions? So here is the holographic dictionary. So a positive helicity gluon is given by the product of a J current from the free fermion sector and a light Liouville operator with appropriate weight, with some normalization factor that I'm not writing down explicitly. And the negative helicity gluon is similarly given by the product of J bar and the same Liouville operator. Remember that J bar is just J dressed with eta, partial eta. Okay, so now it's straightforward to put the correlation functions from the two sectors together. The normalizations cancel as we wish, and we get the spin part multiplying the scalar part, and that's exactly the full leaf amplitude. Okay. So let me summarize my talk. Now let's go from the right to the left. We constructed a leaf CFT that's relatively simple with these two sectors. And with this holographic dictionary, with the free fermion sector giving the spin part and Liouville giving the scalar part, we obtain leaf amplitudes, which are smooth objects associated to individual hyperbolic leaves in flat space. And by putting these leaves together, which amounts to this relation between slasher amplitudes and the leaf amplitudes, we obtain singular slasher amplitudes that are fully Poincare invariant. So with this complete chain, we gave a direct two-dimensional reconstruction of translation invariant for the amplitudes. Okay, so let me conclude with some future directions. We give a nice and simple CFT dual for leaf amplitudes and thus for flat space amplitude, but our analysis is pretty much constrained to tree level MHV gluon amplitudes, and we want to do much more. So, for example, can we go beyond the MHV sector, which some of you already asked about? Can we give analogous MHV rules for leaf amplitudes? And also, can we take into account loops? So this is the paper I was mentioning, who turned on finite B, go to the next order, and showed that the one loop amplitude with the presence of a background source are given by Liouville correlators at finite B. And we might hope to do something similar here. And in my talk, I circumvented talking about the de Sitter slices by saying we can go to 2-2 signature and make up the full amplitude there. But can we give a direct description in Minkowski space? And that requires us to deal with the de Sitter slices directly. Also, can we give an intrinsic definition for leaf amplitude instead of taking a slasher amplitude apart to obtain partial amplitudes on leaves? So this might look like defining a leaf vacuum in which we scatter and obtain leaf amplitudes directly instead of scattering the usual Minkowski vacuum. So in this paper with the same collaborators, we constructed a renderer-like state, which has the right symmetries. So it breaks translation invariance while still preserves Lorentz invariance. So that has the right symmetries for producing leaf amplitudes and serves as a candidate for such a leaf vacuum. Okay, and also we definitely want to repeat all this for gravity eventually. And maybe you have more ideas. Okay, thank you.
Those being, I mean, we could find lift amplitudes for open string amplitudes because they're more complicated, but sometimes they simplify.
Amplitude for open string.
So how would you then go on defining them?
Wait, do you mean like embed the CFT sector into like string theory?
I start with the string amplitudes, do the
Yeah.
Mellin transform and particularize.
Oh, I see.
Just the Venusian amplitude.
Sorry, oh, Venezuela. That's a good question. Do they like the nice thing about MHV amplitudes is they are like local in some sense. Like the interaction vertex is localized. I'm not sure how to explain this in like simple terms, but say you can see in twistor theory, like when you go to twistor space, MHV interaction vertices are like localized, but say like when you go to like next order in MHV, you have like two separate interaction vertices, which makes sense from also like the MHV rule intuition. So do like open string amplitudes have similar properties?
Yeah, it just has a bunch of higher derivative contact interactions, full-point contact interactions.
I see.
I think maybe something that's relevant is when you looked at the MHV formula, there was a factorization of the energy and the like points on the celestial sphere, and that's just not going to happen for the loop for the string amplitudes.
Right.
And
Yeah.
so then
That's right.
it's confusing. That factorization made it so that your dual, right, also had some factorized properties.
Yeah, that's right. I was gonna ask about that, yeah.
Yeah, exactly.
Well, maybe you could learn something if you could interpret the
Yeah.
string amplitudes that way. That would be highly non-trivial.
Yeah.
Yeah.
I have a question related to the point Monica raised. I mean, this factorization between these dual CFTs.
Yeah.
What is the argument, or do you actually expect, like order by order in B, this will stay the same? Like, there's no coupling. You don't have to modify this factorization structure. Is there an argument for that this factorization structure of the CFT will remain? When you consider corrections in B.
In B, okay.
Which is to be consistent with the loop contributions coming from the block.
Yeah, exactly.
Certainly you have to, as you said, from this check that people have done for one loop, you have to, include finite B effects from the CFT, but
Yeah.
maybe you also have to couple them with
Right.
around B.
Exactly. I wouldn't say I expect the factorization to persist because, yeah, like Monica was saying, the tree-level MHV amplitudes factorize in a nice way that allow for this factorization, and also when you go to higher loops, the intuition with having like local contact interaction is also no longer there. So yeah, I think it's likely that there will be a mixing between the two sectors.
I have a very basic question. Suppose you want to do it for SUN instead of SON. Your fermions have to become complex.
Exactly.
But also the eta field has to be changed or not?
I don't think it needs to be changed. Oh, this reminded me of a comment I forgot to make. So
Because they mix the J bar and the J, right? So
Yeah. Let's see. So the main reason we choose eta to be a field of weight minus 3/2 here is such that it has 4 like 0 moles on the sphere. So when we do, so the comment I was gonna make is there's a selection rule here. This is only non-zero when we have 2 J bars. Because with like 4 0 moles, we have to insert exactly 4 etas to absorb the 0 moles, which makes the correlator non-vanishing. And 4 etas come from 2 J bars. Yeah. So when we go to SUN instead, I don't think that changes.
Right.
So
Why not just use bosons? You can take, I mean, it's actually level 1. Just
Yeah.
take the compact bosons.
yeah, because of K11.
yeah,
And -1 compact bosons.
right. Okay, any other questions?
Can you speculate on what would happen for, let's just say, MHV gravity, like the simplest? Do you have any speculation on what the analog of this construction was?
Yeah, not really. Mostly just because the MHV amplitude is like much more complicated. So yeah, without an honest try, I think it's hard for me to really tell.
How is this related to the more general question, like understanding what is the celestial CFT for amplitudes? Do you think this will, is it one way to give a answer to that question, or give you the answer that people have been asking for?
That's a good question.
Or
So
is it like one to, I mean, are you claiming this is the only way to make sense of this pair, or this is just one way?
I tend to say this is one way, and because this whole construction is pretty bottom up, and the thing with the bottom up construction is, it's not like fixed microscopically. With that said, I think there's still a lot of virtue in this example because it's very concrete. It realizes translation variance, which people weren't able to do before. And it's also very simple. And you can definitely like also imagine embedding this CFT into some more complicated CFT or some stringy construction. So it might help constrain the microscopic theory that we're looking for eventually. But yeah, it's still a huge step to get there. Yes, by no way we claim this is unique. Yeah, but it's still nice.
Let's thank Tianli.